Hello, everyone, and welcome to episode 2 of season 1, where we discuss fine tuning neural networks. In this episode, we'll focus on two aspects of the neural network. The first one would be focusing on the input layer and what we can do in terms of tuning it so that we can optimize the network so that it will converge faster. The second aspect we'll study today is on tuning the output layer, where we'll figure out different types of output functions, when to use which one, different types of loss functions, and when to use which one for what use case. So let's get started. Let's start with the input layer first. What are the problems that are there with the input layer? How the input is passed to the input layer. So the first problem is that when you're passing in this input, the dimension of each feature that is passed in could be different. So let's look at the example that's shown in the right hand side. So here we are trying to predict the price of a house given different attributes of the house, like the house size in square foot, the number of bedrooms, and the lot size. And as you can see here, that the price of the house is measured in, let's say, millions of dollars, right? It's about a seven-figure number. And then you have the house size, which is measured in square feet, which is measured in thousands. The number of bedrooms is measured in units of maybe one digit, maximum two digits. And then you have the lot size, which is again measured in square feet, which is in thousands. So as you can see here, the values are very different in terms of their range and in the units in which they are measured. Another similar example would be something that you see here, where the machine or the neural network is being designed to predict the storage IOPS or the performance of the storage for different values of CPU utilization, memory consumption, and the network packets per second. And here again, you see that the storage IOPS is in between, thousands to tens and thousands in terms of the range of values. The packets per second is usually much higher, between tens and thousands to hundreds and thousands. The memory, which is measured in bytes, memory consumption could be much, much larger, millions of bytes. And then the CPU utilization is measured in percentages between 0 and 100%. So that's what's first problem. The units of the features that you're passing in as input could be very different, and the range of values also could be very different. There's a second problem in terms of how the input is passed to the input layer. Let's look at the first example here. In the first example here, you see that during training, you're passing in values that are all positive, and during inference, you pass a value that is negative. Now, the neural network is going to learn during training on all positive numbers, but it has no reference to a negative number. So when you give it a negative number during inference, its prediction is going to be way off. An example with images would be something like this. During training, let's assume the problem that you're trying to solve is training for finding out whether an image has a rose or not. And during training, you pass it a lot of images of roses and non-roses. But of the images of roses that you pass during training, all of them are red. However, during inference, you pass an image of a rose, but the color of the rose is yellow. Now, should the neural network predict that as a rose? I mean, you would expect it to predict as a rose, but it has never seen a yellow rose during training. It has seen different characteristics of roses, how its petals are, and so on, but it has never seen a yellow rose. So it's not going to be able to predict that. So obviously, you would like to solve for these kind of variances in the input. So how do you do that? So before we get into how, let's look at a little bit of data to understand the characteristics of data and how you can essentially get to a solution. So let's assume that this is my input data. I have three features, as you can see, and I've color coded them so that it becomes easy for us to follow along. So you have the feature 1, which is in blue, feature 2, which is in green, and feature 3, which is in yellow. Now, if I were to plot these data points, this is how it's going to look. So the blue dots, as you can see, or the blue data, is going to fall in the top right-hand quadrant of your graph. And if you see the values, the range of values are between minimum of 200 to a maximum of 496, averaging it at around 351.36. Now, the features that are represented in green, if you look at it, they are in the top left and right quadrants, and they have a range of values from 511,000 to a maximum of 790,894, with an average of about 634, 815.44. And as you see, both in terms of its distribution as well as the range of values, the green is very different from the blue. Now, if you go to the yellow feature, this falls under the bottom right quadrant. And if you see, the range of values is between negative 0.05 to a maximum of negative 0.02, averaging it out around negative 0.035. Again, here the yellow, both in terms of its distribution and its range, is very different from feature 1 and feature 2. So this is the problem that you're dealing with. Now let's see, before we get into the math, how we can actually fix this. So let's start with the first feature. So again, I'm going to plot it just like the way you saw it in the prior slide. So this is the original data. So how about I center these distribution or these blue dots closer to the center of your graph, closer to 0. Essentially what I'm doing here is that. So if you look at it, all these dots have been moved closer to the center. What does it mean to move it closer to the center? It essentially means that you are making the average of all these data points 0. Right? You just move everything. You essentially take this data and you subtract it by its average, so everything moves to the center of your graph. So that's the first thing that we do. The second thing that we do is that we normalize or standardize this data, which essentially means that you scale the data down so that you fix the range or the standard deviation of all the data points so that they all are 1. As you can see here, you have centered it here first, and then you have normalized it or you have scaled it using a technique called z-score standardization, where you essentially make the standard deviation 1. We'll learn about how to do that, how to implement it in a minute. But as you can see, you have moved the data from this original distribution to something like this. Now, you want to bring this consistency to feature 2 and feature 3 as well. So the way you do that is you take the next feature. The distribution is the way it is shown here. You first center it, essentially moving everything so that the average comes down to 0, as you can see here. And then you apply again z-score standardization, where you scale the data values down. And you see that the standard deviation is 1 when you apply the z-score standardization. You do the same thing for feature 3 as well. You take the distribution, the original distribution, centered it around 0 so that the average becomes 0. And then you essentially scale it down so that the standard deviation of your data becomes 1. So what we have done here is we have taken this input, which is here in the top, all these three, and then we have standardized it, or it's also called normalizing. We normalize it so that the standard deviation becomes 1 and the mean becomes 0 for all the features. Now we have consistency in how the data is represented. This is what we feed to the neural network. So how do you implement it? The implementation is very simple. The formula for standardization or z-score standardization or normalization is you essentially the first step is you basically compute the mean of all your data. So let's say assume your data is 10, 12, and 9. You compute the average or the mean, which is add up all of these and divide it by the number of samples, which is 3 here, and you get a value of 10.33. The next thing you do is you compute the standard deviation of your data. The way you do that, you take the original number 10, subtract the mean from it, and square it. Now add it to the second sample for that feature. You take 12, subtract the mean from that, and square it. And then you add the next sample, which is 9. You subtract the mean, and then you square it. And then you take an average of that. Because there are 3 samples, you divide it by 3, and you take a square root. You essentially get your standard deviation of 1.25. Now you have to essentially use these two values to calculate the normalized value of your samples. The way you do that is you basically use this formula. If you look at this formula here, or let's just use this. You take the first sample for this feature, which is 10. You subtract it from its mean, which is 10.33, which is what you do here. And then you divide it by the standard deviation, 1.25. You do the same thing, and you essentially get a value of negative 0.27. Now you take the next number, which is 12. You subtract it from its mean of the series, which is 10.33, divided by the standard deviation, and you get 1.34. And you repeat it for the next one, where you get a negative 1.07. So now what you have done here is you have taken these data points and you have essentially both centered and scaled the data. You do that for all the features, right? So if you look at the examples here, I've shown this one already. So let's skip that. Let's go to the next one. You take 200, 250, and 198, which is the second feature. You apply the same thing. First, you calculate the mean, then you calculate the standard deviation for the series. And for individual data points, you essentially standardize or z-score standardize or normalize the data. And this is what you get. Essentially, when you get this, you're essentially taking these numbers 10, 12, 9 and converting it into negative 0.27, 1.34, and negative 1.07 for feature A, where if you look at the average of the normalized data, it comes down to 0 and the standard deviation comes down to 1. For feature 2, the values go from 200, 250, 198 to negative 0.66, positive 1.41, negative 0.75. Again, when you take the normalized values and you take their mean, it is 0 and the standard deviation is 1. Feature C, you go from minus 5, minus 6, minus 4 to 0, minus 1.22 to positive 1.22. Same thing. Essentially, if you were to average the normalized values, the mean is 0 and then the standard deviation is 1. So now you have brought in a consistency in all your input data across all the features. So how would you implement this? Here I'm showing you a NumPy implementation where I take an array of, let's say, 8 values. I calculate the mean using the NumPy method, x.mean, and then I create the standard deviation. And for the entire series, I take the original input, subtract it from the mean of the series, and divide it by the standard deviation. And here you would essentially get xt would be a normalized array, NumPy array of all these values. There's another library that you could use, and that library comes from the sklearn library, where of course you import it and then you create an object called standard scaler. And then you essentially use this thing called fit transform, and this is going to give you the normalized value of your NumPy array. Now, this is great for normalizing input during training, where you have a large set of samples, typically thousands or hundreds and thousands and millions of samples. So you can essentially take an average and create a standard deviation. When you're doing inferencing, you might be interested in predicting from a single input value. Yeah. So, for example, let's say that you were to predict during training, you're trying to predict the price of a house given its square footage and its number of bedrooms and lot size, and you're downloading the data from some real estate website, and you have a sample of 100,000 houses. And during training, you use normalization. You have essentially 100,000 samples, so you can essentially take a mean and a standard deviation. It works great. Now you're applying this learned model or trained neural network during inferencing or prediction. And there you're just giving one value, one input, which is if the house size were 2,400 square feet and it has 3 bedrooms and it's on a lot of 5,000 square feet, what is the price? How do you take an average and a standard deviation from this one sample? You can't. What you do during training is that you continue to keep the running average of your series as well as the running standard deviation of your series. I show you the formula here. And then during inference, what you do is that you basically use these two values, the running mean and the running standard deviation of your entire series that you obtained during training. And then you essentially apply that to create the standardized values or normalized values of even a single data point, which can be used during inference. So that is how you transform your input data so that you would essentially bring a consistency in how the data is processed by the neural network. This is a very important step, and later on in today's presentation, I'll give you a demo of what would happen to the training when you standardize it or normalize it versus when you don't do it. With that, let's move on to the second part of today's presentation. We already talked about how to handle input. Now let's look at output. So in output, there are two concepts that we need to get a good understanding of. One is output functions, the other is loss functions. Now, just as a very quick summary of what is an output function and what is a loss function. So an output function is it takes one or more neurons in the last layer of your neural network. The last layer of a neural network is called the output layer, and it can have one or more neurons. Why it can have more than one neuron, we'll discuss it through the use cases in subsequent slides. But you take this last layer and take the number of neurons in this output layer, and then you use a function which will convert the values that are coming from this layer into a prediction, which we call as a Y prediction. And you could essentially output one value or you could output multiple values. So that is what an output function does. And there are different types of output functions to solve different use cases, and we'll go into that in subsequent slides. The next one is a loss function, which happens here. Now that you have made a prediction, It's quite possible during training that your prediction is off. So, what you have to do is that you need to take your ground truth value, which is coming in from your training samples, and you have to see how off your prediction is from the ground truth value. And that is what the loss function does. It takes both the ground truth value, which is y true, it takes the predicted value from your training, y pred, and it computes the loss or the error. And this error is, of course, used during the backpropagation phase using a gradient descent algorithm to go and update all these weights in each and every layer, weights as well as biases in each and every neuron of each and every layer, so that your predictions start to get better and better, so that your y pred, which is your prediction, becomes as close to y true, which is the ground truth value, which essentially means that your loss essentially converges down to something very, 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 very small, closer to zero. So there are two functions again, output function and loss function. This is what we're going to study today. And the way I want to teach this is, instead of just studying different output and loss functions, let's actually use different use cases and apply these different loss and output functions to those use cases. That way you'll be able to map not just what a specific loss function does, but you'll essentially be able to figure out in which context you have to use which specific loss function. So in neural networks, there are four classes of use cases that you could or problems that you could solve. So the first class of problems is called regression problems. Regression problem is predicting a number. I mean, you can think about it like predicting the price of a house given its square footage, bedrooms, and lot size. That's a regression problem. Then you have a different class of problem called classification problem. In classification problem, you have three subclasses or subgroups. One is called binary classification. That is, you give it a piece of text and or an email, and it can classify that email as spam or not spam. You give it a bunch of transactions, and in a banking transactions, it will say whether a transaction is fraudulent or legitimate. You give it a tweet, a text from tweet, and it's going to predict whether the sentiment of that tweet is positive or negative. So it's a binary classification, A or B. That's what a binary classification does. Then you have a second type of classification called multi-class classification. An example for that would be you give it an image and it says, okay, that image either is a dog or it has a cat or a tiger. Third type of classification problem is called as a multi-label classification, where you're trying to apply labels to your input. And you could have zero or more labels that you could apply to an input. An example would be give it an image, and let's say that image is having a picture of a dog playing with a ball in the yard. And I mean, when you're training it, you would essentially be able to label it training and then inferring it later. You'll be able to label this image as it has a label of dog, as well as a label of outdoor, as well as a label of playing. So that's a second class, right? Classification, a second class of use cases that you could solve. A third class of use case would be ranking, where, for example, you have a question and answer system and you give it four answers and you want it to rank it from the best to the worst answer. It's it's used in large language model training, for example, or it's also used sometimes in search engine where you would like to figure out predictions of how to rank different answers. And the fourth class of problems is called generation problems, which is where you can give it a question like, hey, what is the capital of United States? And it's going to emit an answer, Washington, D.C. This falls under the realm of the transformer architecture and large language models. But in today's presentation, we will cover the first three groups, which is the regression, classification, and ranking. And in season 3 and season 4 of our web series, we are going to cover transformer architecture as well as large language models. And that's where we'll study the generation problem. Now let's get into the first one, which is the regression problem. So what is the use case here? Use case here is you'd like to predict one or more output numbers given one or more input numbers. We took this example earlier. Example would be you want to predict the price of a house given its features like square foot, bedrooms, and lot size. Or you would like to predict, for example, the CPU and memory utilization when the storage IOPS and the network packets per second is some value. Now, the obvious questions here is, how many neurons do you think you would need in the output layer for solving this use case? And what would be the right output function? And what would be the right loss function? So let's jump in and see. So the first use case would be what we call as a single output regression. Single output regression. In single output regression, as the name suggests, you're trying to predict one output value. I'll go back to our prior example. What is the price of a house when the square foot is 2700 square feet? Bedrooms is 3 and the lot size is 7600 square feet. You're predicting only one value here, price. That's why you have only one neuron in your output layer. How many inputs do you how many neurons do you have in your input layer? You want to have 3. Why 3? Because your input features are 3 here. Square feet, bedroom, and lot size. Square feet, bedroom, and lot size. Yeah. There's a second type of regression use case, which is multi-output regression. Here you're trying to predict, for example, what is the CPU and memory utilization of my system when I'm seeing about 13,000 packets per second coming over the network, and the disk is taking about 9,500 IOPS. So you're trying to predict two values, CPU and memory utilization. That's why you have two neurons in your output. How many input neurons do you have? You have two neurons in the input layer, network and storage. Network PPS, packets per second, storage IOPS. So single output again is predicting one output, multiple output regression predicting multiple outputs. Now let's look at a little bit more detail. Let's use our again same example of predicting the price of houses. So here I'm in the training phase where I have my samples, and like we discussed earlier, we are going to normalize all the inputs. The inputs are fed to the input layer, and we already discussed that the input layer has three neurons because these are the three features: the square feet, bedroom, and lot size. And we created a neural network of multiple layers, and each layer could have multiple neurons. As an example, I just show you one hidden layer in between. And then, of course, there's only one output because it's a single output regression because you're only predicting the price of the house. And then you have your output function here, which predicts the value. So, what is fed to this output function? Just as a recap, the activations values that come from the individual neurons at the hidden layer, let's say A1, A2, A3, A4, A5, go to the output neuron, and you calculate the value of this logit here. We saw this in episode 1. Just as a recap, you calculate the Z1 as you take this activation function value from this neuron A1, multiply it with its weight W1. You take the value of the activation coming from the second neuron A2, multiply it with the weight W2, and A3 multiplied with W3, A4 with W4, A5 with W5, and then you add the bias value in this output neuron here, and you add up all of these things. That is your value of your logit. In the output layer, typically there is no activation that's applied. So essentially the activation value here is the same as your logit value. And you should go back and refer to our episode 1 where I talk about what these Z's and H's mean. So I would strongly encourage, if you're not done that, to go back and look at that, because that's, I think it's critical to follow that, use that nomenclature to follow along in today's presentation. So anyway, so we take this value. So essentially what is coming out of here, this neuron here, is the H1. Output function that you'll use for regression problem is what is called as a linear function. So what is a linear function? A linear function is basically does not do any transformation. It just takes exactly the value that comes out from here and forwards it forward as a prediction. So your linear function takes your Z1 and essentially makes that your Y pred. Now the loss function, essentially, let's say is a true ground truth value and this is your prediction value, correct? Now you have to figure out how off your prediction is from the ground truth value. For that, you have a few options in terms of loss functions. One very commonly used loss function is called MSE, which stands for mean squared error. It's very simple. Essentially, you take the true value, ground truth value, which comes from your training sample, you subtract the predicted value from it, and you square it. Yeah, that's what the mean squared error function does. And from this comes the value of a loss. Now, this loss then is used during using a gradient descent algorithm to go fix these weights and biases and all the weights and biases in this layer as well. Now, let's go to the multiple output regression. Now, you're trying to predict more than one value. And the way you do that is you essentially, okay, in this case, you're trying to predict the CPU and memory utilization given the network packets per second and storage IOPS. So again, you normalize all the input. You have two neurons in the input layer corresponding to the network PPS as well as storage IOPS. You have a bunch of hidden layers and a bunch of neurons within those layers. As an example, I show you two layers, layer 1, layer 2, and they essentially have these many numbers and neurons in them. And the output essentially is going to be two neurons again, because CPU and memory are two predictions you would like to make. So here, each of these neurons, I show you the weights W1 through 3 and 4 through 6 here, and of course their individual biases. So you would calculate the logit values exactly like you saw earlier. You take A1 multiplied with W1, you take A2 multiplied with W2, A3 with W3, and add the bias, add all of them. So that would be the logit value for this neuron. For the second neuron, you take A1 multiplied by W4, A2 multiplied by W5, A3 multiplied by W6, and then add all of them with the bias B2. And like I said, in the output layer, the logit value is what you pass along. There's no activation here. The output functions still remain linear functions like we saw in the single output regression use case. Now the loss function again is mean squared error. So which means that you take the difference, which is y true 1, ground truth value, subtract y pred 1 from it. That's what you do here, square it. You take the second output value, y2, the ground truth value, and subtract the predicted value, square it, add them up, and divide by 2. Y2, you essentially have two values that you're predicting here. That's why it's called mean squared error. There are other types of loss functions as well. For example, root mean square error and so on. So this is how you would solve for the single as well as multi-output regression use case. This is a good summary of it. Key thing to remember, if you have one value to predict, you have one output neuron. You have multiple values to predict, you have as many multiple output neurons. The output functions are linear functions, and the loss function is mean squared error or root mean squared error, and so on. Now let's look at a demo. So this is the demo of, let's start with a single output regression problem. So I have created a Jupyter notebook. Let's start by first, loading and importing the different types of modules that we want. We are essentially importing the Keras library and so on. Now, what I have created here is a function that will generate some data for us. Essentially, what it does is that it takes different ranges of square footages of houses and price ranges, and it just basically makes a data set for us. You don't really have to go into these details because it's not relevant for understanding how to use these libraries to do the prediction. Okay, so just assume that there is a function that will generate the data for you. Let's execute that. Now, first thing we do, as I said earlier, is that we have to normalize this data. So I'm using the standard scalar from the sklearn library. I've created one to normalize the input features, one to normalize the output feature. So let's execute that. Okay, now let's look at building this model. In this model, I basically create a sequential model using the Keras library. What this does is it basically creates a linear dense neural network. And then to this, I'm adding a hidden layer. In this hidden layer, I'm essentially adding 10 neurons to it, in this layer. I could choose 10, 5, 4. You can experiment with different values. There is no one formula that will tell you what is the right number of layers or what is the right number of neurons per layer. But anyway, let's say we are adding one layer here, one hidden layer with 10 neurons in it. And the input dimensions is 3. The reason it is 3 is because we are essentially giving square footage, which is 1, lot size is 2, and bedrooms is 3 as your input. So the input dimensions is 3. And I'm using an activation function called ReLU. We'll go into more of what these activation functions are and the specifics of each one in episode 3 of our presentation. And also skip this thing called he normal here, which is again something that we'll study in episode 3. This is essentially allows you to initialize the weights in a certain way. But coming back here, you have created a model, a neural network model, you have added one layer, and in that layer, you're adding 10 neurons. Input to that layer is, of course, 3 because you have these 3 as your input. Then you're creating an output layer with a single neuron in it. And I've not given any activation, I've not given it a output function name. So essentially, it's assumed to be a linear function. Okay. Now I compile this model. The loss function that I'm using for this model is MSE, which stands for mean squared error, which you already saw. Okay, so I essentially build this model here. Okay, now I have this model. Now let's generate some data. I'm generating about 10,000 samples, and I'm pretty printing it here, so you can see there are 10,000 samples here. The square feet of your different houses, the number of bedroom for each house, the lot size, and the price. Okay. Now we'll use this data for training our neural network. So let's go ahead and train our neural network. So the first thing that we do is basically we take the model, and then before you essentially start fitting this data into this model, you have to normalize this input. And that's what we do here. We are essentially using the standard scalars fit underscore transform library, and it is going to do the normalization for you. Okay, so I've normalized input, and then I'm going to pass it to our Keras fit utility, which will essentially start doing the training. We run our training for 100 epochs, and we use mini batch. So essentially, we're using a batch size of 10. Okay, let's run this. As you can see here, that is the loss from your first epoch, the loss from a second epoch, the loss from a third epoch. And as you can see, as the number of epochs is increasing, the loss is decreasing, which essentially means that the neural network is starting to learn the pattern that fits this data. Yeah. So let it go through. We'll give it some time. All right. So our training is done here. And as you see at the 100th epoch, our loss value is 0.0381. Now let's move on to making some predictions. And again, what I do here is I basically generate 20 more random samples. I mean, like this is just so that we can test it out. And then use those samples to make some predictions. We only use, by the way, we take these samples that we generated, again, we normalize, and then you pass it to the model so that it can predict. Is it model.predict? And then you just pass, of course, just the input. I mean, you don't have to give it the ground truth value. We'll still get the ground truth value, so we'll know how well we are done relative to the ground truth value, right? But as you can see here, only the X or the 3 input variables are passed. Yeah. And this is how we capture the predictions. And then you're going to reverse transform normalize the Y predicted values, right? And then we compare. Okay, so let's run this predictions. So the prediction is done. All right, now let's pretty print our predictions to see how well we have done. So these are the values, 20 values for which you are doing the prediction. And these are the number of bedrooms, lot size. And this is supposed to be the value of our prediction. What we predicted is this. We are just off by 2%, which is for a very small sample set and for just training this model for just a minute or so. I think we have done quite well. If you look at this, if the house price were the square footage of your house was 3,339 square feet, and it has 4 bedrooms and it has a lot size of 5890 square feet, it is predicting our model is predicting that the house is about 2.81 million. It should actually have been 2.86, which is just 1% off, which is, I think, pretty good. Yeah. So as you can see, I think we are done quite well. We are 2%, 1%, 3%, -8. We'll come to that in a minute. 3%, 4%, right? If you had more data or you had trained it for longer, you'll start to see that we are getting much closer in terms of aligning our predictions to what the value should be. The reason you see that some of these places you see higher divergence from what the predictor value from what it should be. Like for example, here it's -8%, there is 6% and 12% and so on, 7%, is primarily because we have our random generator did not generate sufficient training data within that particular combination of square footage, number of bedrooms, and lot size, and so on. If you had a much larger data set with which captures even these ranges well, then you would essentially see that even their values would be much smaller, like 1% off or even less than 1% off. So as you can see, just as a very quick recap, creating the model is pretty straightforward. Let me hide this here. Okay, so creating the model is pretty straightforward. We have just created one hidden layer with 10 neurons in it. We pass the three inputs to it. We use an activation function called rectified linear unit, ReLU. We just add one neuron to the output layer, and then we use a mean squared error loss function. Then we essentially normalize the input. We pass it to model.fit, and it essentially does the training for us, and then we go ahead and make the prediction. It's very simple. Now let's look at how to do the same for multi-output regression problems. All right, let's look at a demo of multi-output regression. So just like in the prior example, we are going to import some libraries, some TensorFlow, Keras libraries, NumPy, and so on. And then we're going to use the same data generation function. This time, instead of generating just one output for three different inputs, it's going to take two inputs, square footage and lot size, which are your two input features, and it's going to predict two numbers, price as well as bedrooms. So what would be the price of a house and the number of bedrooms if its square footage were some number that is represented by this, and lot size is represented by this. So two outputs, two inputs. So we can skip the logic behind how this data is generated. You can look at it later, but it's not relevant to understanding how the model is built. Okay, so let's skip this part. Again, let's create a standard scalar library so that we can normalize our input. Now let's build out our neural network. Again, we'll create a sequential neural network. We'll add again one single hidden layer, 10 neurons in that layer. Input dimensions is 2, why 2? Because you're passing in just the square footage and lot size. So two inputs. Again, we're using the activation called ReLU, activation function called ReLU in that hidden layer. For the output, you're predicting two values. That's why you have two neurons in your output layer. One is the price, the other is the bedroom, number of bedrooms. I compile the model, and we again use the mean squared error loss function here. Okay, let's go ahead and run this. Okay, now let's generate some data. Again, we're going to generate about 10,000 samples. The input here is square footage and lot size that you can see here. And the output is going to be ground truth values are here, which is Y's are Y price and Y number of bedrooms. Okay. Now let's go ahead and train our model. Same thing, you essentially normalize the input and pass it to the model.fit. We'll run it for 100 epochs at a batch size of 10. Let's go ahead and run this. So you see that after the first epoch, our loss is 0.1549. And the second epoch, it has dropped to 0.133. Third epoch, 0.1184. So as you can see, the loss value is decreasing, which is great, which essentially means that our model is able to fit this data. In other words, it's essentially the training, and the training is converging quite well as the loss is dropping as we are increasing the number of epochs. Again, just as a recap, an epoch is one full, exposure of your entire training data set to your model. That is one epoch. You give the entire data set again for the second time, is a second epoch. Again for the third time is a third epoch. So epoch is an entire exposure of your data set, training data set to your model. So we are right now at the 27th epoch, and let's see where the loss is at 0.0571. It is continuing to drop. That's good. And sometimes you see it increasing, which is fine. Again, it is converging, it's coming down. I mean, there are other techniques to bail out early if your loss is, it's gone down and goes back up again. We'll study this in episode 3. But for now, let's just wait for all the 100 epochs to be done. We're almost getting there. We are at our 99th epoch. So we are at the 100th epoch. And there it is. We have trained our network. And as you can see, at the end of the 100th epoch, our loss is 0.0529. If you had more data and you ran it for more epochs, then it would have even fallen down below. Ideally, we would like to train it so that our loss falls down to something like 0.001 or something like that, which is pretty low. Okay. Now that we have done the training, let's go ahead and make some predictions. Again, for that, just like in the past, I'm going to generate some data points. This will allow us to compare how our predictions are relative to the actual value that they should be. Okay, that's the reason I'm using the same function to generate the data so that I can do the comparison and the validation. Okay, and just like in the past, as we explained, we have to normalize the input like we normalize it during training. We use the library that do that, extra transform. We make the prediction using model.predict, and you only pass the x values, which is the square footage and the lot size. Obviously, the predictions are going to have how many values? Two values, the price as well as the number of bedrooms, because that is what we are trying to predict here. And we denormalize the predictions using the inverse transform library function. Okay, so let's run that. Now we're going to predict. Inference is usually very fast. As you can see, it has finished the inference for 20 samples in 96 milliseconds. And now let us go ahead and pretty print our results and see how we have done. All right, let's walk through this. So we have 20 uh, numbers that we want, or 20 samples or data points that we would like to get predictions for. So the input is square footage and lot size. These are the first two columns. The expected ground truth value for the price that is to be predicted is here is 1.16 million, and our model predicted as 1.37, right, which is off by about 17%. Not great, but let's just stick with that for the moment. Okay. The expected number of bedrooms is 3, and our model predicted as 2, which is off by about 10%. Again, this is not a great outcome for us. The predictions are off by more than it's a double-digit percentage off. So let's go to the next one. Let's actually pick this number 2 here. Okay. For the lot size of, sorry, the square footage of a house for 2694 square feet, sitting on a lot of 3234 square feet. The expected price of the house is 2.83 million with 3 bedrooms. And what our model predicted is the price, instead of the price being 2.83, it has predicted 2.79, which is just off by 1%, which is great, which is very pretty close. The predictions are pretty close, right? For again, given that we just ran the training for just a few minutes on just 10,000 samples. Imagine if you had 100,000 samples or a million samples and you ran the training for an hour or so, you'd essentially converge even better. But even for such a small training sample as well as training time, this is 1% off. It is supposed to be, the number of bedrooms is supposed to be 3. Our model predicted as 3. That's great, which is about 0%. We are pretty much consistent with that, right? And so on. As you can see, let's pick another one. Let's say we pick this one here on a house that is 4,310 square feet in size, sitting on a lot of 6,034 square feet. The value is supposed to be 3.4 million. Our model predicted 3.2 million, which is about 5% off. It can do better, but again, if you give it more data, it would do better. But it predicted the number of bedrooms pretty accurately. It was supposed to be 5 bedrooms, it predicted 5 bedrooms, right? So that's great. So again, just as a quick recap, as we can see here, doing the single output or multi-output building the model and predicting is pretty straightforward. You use the sequential model of your Keras library. You added one hidden layer. You could add multiple, but given that our data set number of features is small, actually you don't benefit much from adding a lot more layers or adding more neurons. You essentially pass the number of inputs on which you would like to make the predictions. It's an input dimension. You typically use an activation function called ReLU. You could use other ones too, which we'll cover in episode 3. But ReLU is pretty much a very popular and a go-to activation function for many use cases. So let's use ReLU here. And then you add an output layer, and you add as many neurons in this output layer as the number of features that you're trying to predict. In the multi-output, you're predicting both price and bedroom, so it's 2. In the single output regression use case, you're predicting just the price, so it would have been just one neuron in the output layer. And we compile the module, the model with the loss function. You're using mean square error here. I show an optimizer called Adam. We'll not cover it here. We'll cover it in episode 3. But this essentially makes the gradient descent algorithm go faster. That's an optimizer. We'll discuss more about that in episode 3. So you compile the model and then you pass it the training data and you fit the data to the model, or you fit the model to the data using model.fit, and then you start making the predictions using model.predict. Just make sure that you are normalizing the input when you're passing it to your model. So that completes our demonstration of how to solve for the regression use case using deep neural networks. We have seen both single as well as multi-output regression use case. Now let's look at the next use case, which is binary classification. So what is binary classification? In binary classification, you're trying to build a model which will predict one of two possible outcomes given an input. Essentially, what you're trying to do is it's trying to take your data point and it's trying to categorize it whether it belongs to category A or it belongs to category B. So, what are some examples where it's useful? Anomaly detection. So, you have a CPU spike on your server. Now, you'd like to figure out whether that CPU spike is an anomaly or it is normal. You give it an email. You want to determine whether that email is spam or not spam. You give it an image. Does that image have a dog or does it not have a dog? Give it a bank transaction. Is that transaction fraudulent or is it valid? Or, for example, you give it a tweet and it analyzes the tweet and says, is the sentiment in the tweet positive or negative? So the key point here is there are only two possible outcomes. Either it is A or it is B. It can never be A and B. It is A or B. It has to be one of those two. That is the reason why it's called binary classification. Now, obviously, there are a few questions that we need to ask ourselves. As you're building this model, how many neurons do you think will be there in the output layer? And what would be the best output function for solving for binary classification? And what is the best loss function? Before we jump into the model, I would like for you to take some time to look at what is there on the screen here, the problem that we are trying to solve for, and come up with your rationale as to how many neurons you think will be in the output layer. Again, we are trying to predict whether a data point belongs to category A or B. Do you think you have to have one neuron, two neurons, three neurons, or more? You would have exactly one neuron. The reason is you either are predicting whether the data is in category A or B. So, which means that you just need one output neuron, and that output neuron should emit a value of 1 or 0. 1 means it belongs to that category A, 0 means it belongs to category B. 1 means it is spam, 0 means it is not spam. 1 means it has an image of a dog, 0 means it does not have an image of a dog. 1 means it is a fraudulent transaction, 0 means it is not. So it's a binary. So you just need one neuron. Okay. Now let's take an example here. So here what we are trying to do is you would like to take some banking transactions and you have the credit score of your customer, you have the age of your customer, the tenure, how long the customer has been with the bank, their current account balance, do they have a credit card, and have they been active in the last 3 months doing transactions, maybe ATM transactions, deposits, and so on. What is their estimated salary, which you might have gotten at the time when they're applying for, getting, applying to get an account in your bank? Are they carrying any debt? And you're also basically, you're training it, right? So you need to have what you're trying to predict. And what we're trying to predict here is, given these attributes, is there a risk that this particular customer can churn, or which means that they will leave your bank? That is what the bank is trying to predict. And 0 means, in this particular training sample, it says, no, they have not churned, which is they are continuing with your bank. 1 means they have churned, which means they have left your bank. And obviously, the bank wants to build a model based on the transactions, and they would like to figure out the risk that a particular customer might carry. And when they are still an active customer, you would like to do certain things so that they don't churn. Yes, that's what you're trying to solve for. So you're predicting again one of two possible outcomes. Are they going to churn or are they not going to churn? Churn means a value of 1, not churn means a value of 0. Okay. Now, how many input neurons will be there in our input layer? How many inputs are there here? Credit score is 1, age is 2, tenure is 3, bank balance is 4, does he have a credit card is 5, are they active in the last 3 months is 6, estimated salary is 7, debt is 8. So you have 1, 2, 3, 4, 5, 6, 7, 8 neurons. How many output neurons? As I said, in binary classification, you have to emit either a 1 or a 0. So you just need 1. That's why you have 1 neuron here in the output. Okay. Just like in the, and by the way, you can have any number of hidden layers. In this picture, I show you 2 hidden layers. It could also have 1. The number of neurons in the each layer, again, there is no fixed rule for that, but we have picked some here. Now you normalize the input like we talked about earlier. This is very critical that we do, because if you see the scale of the individual features is very different. The salary and debt is larger numbers. The credit, whether they have a credit card or not, is a binary number. Account balance is again a large number. Tenure is measured in years or months. It's a small number and so on. Yeah. Okay. So what we are trying to figure out here is what is the best output function and what is the best loss function. The best output function is what is called as a sigmoid function. So just like in the prior examples, the way you calculate the value here from the output neuron is you take the activation coming from the prior hidden layer, A1, multiplied with W1, A2 multiplied with W2, A3 multiplied with W3, and so on. And then you add up everything and add the bias, and that becomes your value that you pass to your output function. What is that output function? Sigmoid output function. So let's understand what the sigmoid output function is. So in the sigmoid output function, you get the logit value that's coming from your output neuron. And what you really need to do, as I said, our goal is to predict a value of either 1 or 0. Yeah. And this summation value could be a very large positive or a negative number. Yes. And how do you make it either a 0 or 1? Sigmoid helps there. What a sigmoid function does, and as you can see, I have shown the value here. What a sigmoid function does is it takes a value and it computes another value from here. And that value that it computes basically squashes any value that you pass to this function between a 0 and 1. Okay. No matter how large a value or how small a value you essentially pass to a sigmoid, what comes out of a sigmoid function is a value that is always between 0 and 1. Some floating point number between 0 and 1. Yes, which actually is very helpful for us. As long as you can squash it between a number between 0 and 1, now you can essentially put some logic and say, hey, if it squashes it to a value between 0.5 and 1, I would say I'll emit a value of 1 as ypred. If it squashes it to a value less than 0.5, and you know that it cannot be lower than 0 because sigmoid always squashes a number between 0 and 1. If it's less than 0.5, I'll say it is 0. And by the way, that threshold of 0.5, it's up to you. You could say a value that is greater than 0.75, I'm going to call it as 1. A value less than 0.75, I'm going to call it as 0. Or a value greater than 0.9 as 1, and a value less than 0.9 as 0. It depends on the use case that you're trying to solve for. You get to decide what is going to be a threshold. But the beauty here, if you think about it, what has the sigmoid function done? The sigmoid function allows you to take any arbitrary sized value that comes from your output layer. It allows you to squash it into a manageable 0 to 1 range, and now that gives you a binary 0 or 1 answer. Beautiful. What about the loss function? Now, the loss function is what is called as a binary cross entropy loss function. So, what you do here is you take the ground truth value, which is y true. You take the predicted value. Again, the predicted value is coming from the sigmoid of the value that comes in from this logit. And then you pass it through a function that looks like this. You take the ground truth value, you multiply it with the log of the predicted value. Then you add it to 1 minus the ground truth value and log of 1 minus the predicted value. So that is how the binary cross entropy function works. Actually, if you think about it, The value of y true can be only either 1 or 0 because you are solving for binary classification, right? It can either be 1 or 0. So let's look at this function. If it actually, let's look at it here. Okay, let's look at this. If y is true, y true is 1, which is essentially your ground truth value is 1. Yeah. And your prediction is 0. Remember that the prediction, what you're getting out of the sigmoid function here is a floating point value, correct? So let's say it's coming out to be, and the floating point value can be between 0 and 1. It's already established, right? So your ground truth value is 1, you predicted 0. Your loss is pretty high because you're predicting exactly the opposite of what actually the ground truth value says. It should be 1 and you're predicting 0. So the loss function basically gives you a value of 34.54, which is large. Remember, our loss function should be very, very, very small, ideally 0.001 and so on, right? Let's say that your prediction, your ground truth value is 1, your sigmoid function predicts 0.1, loss has gone down, you keep going down. Now, if the ground truth value is 1 and you predict 1, the loss is 0. So we have essentially, our prediction is pretty accurate compared to what the ground truth value is. So if the ground truth value were 0, the exact opposite would happen. And you predict 0, the loss is 0, it's all correct. If the ground truth value is 0 and you predict 1, your loss is 34.54. That is what a binary cross entropy function does. So what we have established is for a binary classification use case, we use the sigmoid output function and the binary cross entropy as our loss function. Now let's look at a demonstration of binary classification use case. So we'll start first by initializing our Jupyter notebook and importing a few important Python modules. Let's do that. And then here what I've done is I've created a few helper functions that will allow us to generate some data that we'll use to train our model. You don't have to look at the specifics of the functions here. I mean, you can look at that offline, but just keep in mind that I have three different functions. One function generates data where the samples are, they form a circle. And what we like to identify is for the testing phase, we would like to see if a point that we use to test, does it fall within the circle or outside the circle. Similarly, I have other utility functions that will draw a rectangle and we do the same thing. Given some training testing data set, does the point fall within the rectangle or not? Or here I have a function that does the same for a triangle and so on. So let's run this. So this one just basically defines all these functions. And I could pick the type of geometry of the figure that I'd like to use to generate these data samples for training. All right, so with that, let's actually generate some training data. And here, as you can see, I'm trying to generate data that falls within a circle. So this is a good example of that. So if you notice here, this is a circle, and this circle is, of course, the points within the circle are colored green, and anything that's outside the circle is colored blue, which is very nice because it essentially allows us to do binary classification by using a data point, let's say somewhere here, right? If I were to give this data point, our model should basically predict that, if the point is here, then it should be colored green. And if it is somewhere here, then it should be blue. Binary, either it's here or there, right? So binary classification. So let's go with this example. So I have created this data set, and it has a data set of 5,000 data points, and it is color coded so that some points are within a circle are colored green and outside are blue. Okay, now let's define our model. So as you can see, I'm creating a three-layered neural network. I have two hidden layers. The first layer has 32 neurons. I'm using ReLU as activation function. The second layer also has 32 neurons, and I have the ReLU also as an activation function. And the output, as we saw in a binary classification use case, you just need to have one neuron in your output layer, and that's what you see here. And the activation function or our output function is a sigmoid function, because if you remember, a sigmoid will basically generate a value between 0 and 1, regardless of what values come from the layer just prior to it. So this is a very good activation function for us. Now I compile the model here. And as you can see, the loss function I'm using is the binary cross entropy function. Okay. Now let's train our data set, or let's train our neural network using the data set that we just generated earlier. I'm training it for 100 epochs and I'm creating a batch size of 32. And let's go ahead and train it now. Okay, so first epoch, the loss was 0.4698. Second epoch, it is 0.3055. It's nice. As you can see, the loss is going down, which means that our network is converging. It's learning. So let's just wait for it to finish its 100 epochs. We see that the loss is continuing to go down, which is good, which means that our network is training, it's learning well. All right, so we are done with our training. We have reached our 100th epoch, and as you can see, the loss is 0.0135. Okay, now let's go ahead and see how we have done in terms of training or how our neural network has learned. Okay, so what I do here is I basically generate some data points. Again, the specifics of how it is generated is not really relevant to this, but you can look at the code offline. So I do that and I generate this what I call as X test, and then I pass it to the model.predict. And again, what I do here is I basically say, remember that we use a sigmoid as our output function. And what I'm saying here is that if the value from the sigmoid output function is greater than zero point 0.5, I'll treat it as true. Otherwise, I'll treat it as 0. 1 or 0 is the binary classification, correct? And then we're going to plot this. Now, let's go back to the data once over here. Let's look at this. So if you look at this is our training data, correct? And if you look at it, the values on the X are or feature 1 are between -10 and +10, and on feature 2 is between -10 and +10. And what we want to do is if you just look at the circle here, more or less, if the value of feature 1 is between zero point 0.5 and positive zero point 0.5, and if feature 2 is between negative zero point 0.5 and positive zero point 0.5, anything within the negative 5 to positive 5 in both directions should be colored green. Anything outside should be colored blue. Correct? Now let's go ahead and run this prediction or inference here. Awesome. So it has made this prediction. So what this, of course, the test data generation utility does is it basically generates a line with different points on that line. Now let's see what happens to the different predictions. Anything, as I said, between zero point 0.5 and positive zero point 0.5 in both these things should be green. This is the right this the circular area, and as you can see here, closer to the center it is generating green as it should, and everything outside it is generating blue. Ideally, it should have generated. I mean, it should have colored this data point as well as maybe even this data point as green. But that's fine. I mean, our loss is not really that low. It was zero point 0.0 something, right? If it's much lower, and you would essentially have seen this, it has learned more. Maybe if you had generated more data points during training or you had ran it for more epochs, you would have essentially made this model learn it more accurately. But it has done quite well. Now I'm going to generate um, some random data points instead of a line. So essentially, these data points are scattered all around, and let's see if it's able to predict points within the circle as green and outside it as blue. Okay, let's run that again. So as you can see, let's actually generate many data points. Let's generate 100 data points. Okay. Now, as you can see, between negative 5 and positive 5 on both these features, it is generating it as green. Everything else, it is generating it as blue. So, as you can see, with just a few lines of code, we are able to build a neural network that is able to do binary classification. Let's try something else. Let's try, instead of generating circle, let's try generating a triangle. Okay. So there's another data set, and what we have done here is that we have created a triangle, and any data point within this triangle is going to be colored. Let's say, we treat it as green, and anything outside we treat it as blue. I mean, you could actually map it to a real life use case too. Think about this as radiology image, an X-ray image, where you see a lesion, and the lesion is in the image is marked in this triangle here. And what you're trying to train your neural network is to basically say anything within this triangular area is basically a cancerous tissue, and anything outside is not. Yeah, so that's something would be a more natural, realistic use case that maps to something that we are seeing here. Okay. Now that we have done this, let's go ahead and train our neural network again. Okay, let's build, and now let's train our neural network. So as you can see, we started with a loss of 0.2480, and the neural network is converging. Essentially, it means it's learning. The loss has gone down to 0.019. Let's wait for 100 epochs till the training is done. In a realistic use case, you would train it for much larger data sets and for much more longer epochs, but for our demonstration purposes, this should be fine for now. You would want to typically train so that your loss falls below 0.001, which of course requires us to have quite a bit more data also, training data also. Okay, we are done with our training, 100 epochs done. As you can see, our loss is now 0.0119, which is reasonably low. Okay, with this done, now let's go ahead and generate some test data as well as do some predictions. Remember that in this case, we are trying to predict if right, we are trying to predict, given a few data points here and there, will those data points be colored green or will they be colored blue? Yeah, and if you look at this picture here, anything on feature 1 between -10 and let's say 0, and on the Y feature, anything between 0 and +10. Somewhere within that would be your green dots, and anything outside would be blue dots. Okay, let's go down and now run our prediction. As you can see, anything between -10 and 0, and between 0 and 10 is colored green, and anything outside is colored blue. So as you can see, our neural network that is trained to do binary classification is able to do a pretty good job of predicting whether the outcome is a 0 or a 1. Okay, just to summarize, for binary classification, we use the sigmoid activation function. The idea here is that whatever values flow from the last layer to the output layer, we squash the value between 0 and 1. That acts really good for us to predict a value between 0 and 1, or a value between either 0 or 1. And the loss function we use is the binary cross entropy loss function. Building the network is very simple. You essentially have multiple hidden layers with as many neurons as you think are appropriate. The activation function I use is ReLU, and then the output function is sigmoid, and the loss function is binary cross entropy function. Now let's move on to the second type of classification use case, which is what we call as a multi-class classification. So what is a multi-class classification? See, in multi-class classification, you're trying to build a neural network that can slot an input into three or more possible categories. This is critical, three or more possible categories. If it is two categories, then it becomes binary classification. It's either this class or that class. But if you have more than three, then three or more, then you essentially use a multi-class classification. So what are some good examples of where this is useful? So text classification, for example. So let's say that I want to give it an input text, and I'd like for the model to predict whether the sentiment that is captured in the text is either positive, negative, or it's neutral. So three classes. So it has to classify into one of these three. Image classification. I give it an image and I want it to classify it as, okay, this images of a dog or a cat or a rabbit or a tiger or a monkey. So you have five different categories or classes, and it has to classify it into exactly one of those five. Risk classification, you give it a transaction, it basically classifies it as high risk, moderate risk, or low risk. Again, you have three classes or categories here. So the key point here again is it has to have three or more possible categories. And that's when you use a multi-class classification. And it's very, very important to understand that it only classifies the input into any one of these three or more categories. It cannot do it for more than one. For that, you would use a multi-label classifier, but that's what we'll discuss next. But for multi-class, it has to be three or more possible categories, and it has to classify the input into one of these three, at least one of these three or more classes or categories. So obviously the questions are, how many neurons do you think would be needed in the output layer? And how would you describe the y true value, especially given that you're saying that you have to take three or more classes and then classify the input into that. So first we need to understand, how do you provide this three or more as a ground truth value, right? Or do you use an array? Do you use a scalar? What is it that you use? That's something that we need to understand. And of course, what is the good output function and what is a good loss function for this? Okay, let's go ahead and look at that. So let's look at a few examples here again, just as a way to understand how you build a neural network. Here, what I have is I have a bunch of user reviews of an e-commerce site, and for training, I'll basically say positive, negative, neutral are the three classes, and I build a neural network. So the number of output neurons is going to be three. Why? Because you know that the number of classes into which this input can be classified is one of these three. So you have three here. Okay. Now, similarly, if you have a bunch of images here, and let's say that the classes are, dog, cat, tiger, rabbit, or parrot. So you have five classes here. So how many output neurons do you need in the output layer? Five. Because what you want is the input comes in here, and then one of these things lit up saying that, okay, I think this image is, for example, if you were to give it this image, it would be this particular output neuron will lit up and say, hey, this is a dog. If you were to give it this image, then a well-trained network would basically make this particular neuron activate and say, hey, it's a tiger, and the rest of them essentially will be subdued. So as many number of classes that you would like to classify your input into will be the number of neurons that you will have in the last or the output layer. Okay. Now, uh, let's look at the model here. First thing that we need to understand is, how do you represent these classes? The way you represent these classes while training, because you have to provide it as a ground truth value, is that you use an array or a vector. And how many elements in that vector? The number of classes that you would like to classify into. Let's say that in the prior example of the e-commerce site user reviews as positive, negative, or neutral, there are three classes. You'll have three items in your um, array. Okay. And similarly, you have to essentially have your output function emit an array of the same number of elements. Because you had three here, you're going to have three here. Okay. Now let's look at what would be a good output function. So, first thing that you need to understand, let's go back to this. The ground truth value, only one of them has to be positive, or one of them has to be activated. The remaining are not activated. Why? Because as we said, in multi-class classification, you're classifying the input into one of the three or more categories. So which means the other categories into which you're not slotting the input have to be turned to zero, and only the one in which you're classifying the input into needs to be turned on. So we make it as one. Okay. Now, what you want to do is these three output neurons, because you are classifying into three classes, need to essentially activate based on what you think is the correct correct class or correct category. So the output function we'll use is what is called the softmax output function. What a softmax output function does is, this neural network, the input goes through multiple layers and multiple neurons, and it comes to the output layer. And I mean, the output layer is what? It's basically, again, a bunch of numbers, right? You're essentially calculating Z1, Z2, and Z3, which are your logits here for each of these output neurons. So 5.1 for the first neuron in the output layer, 2.4 for the second neuron in the output layer, and 7.8 in the third neuron in the output layer. Now, this is your, the logic that is calculated. Now, when you feed it to the softmax function, what it does is it basically says which of these values should be activated, or which of these should I turn on and the remaining off. So the way it does it is using this function here. Okay, this mathematical function here. It basically takes e to it raises the power of e to each of these individual things. All right, z1, z2, z3, and then it divides it by the sum of the e's of, this value and this value and this value. Okay, so what it emits is these values. So when you take this array and you pass it to softmax function, it emits an array like this. And as you can see, it basically is saying that z3 should be activated, 7.8. Okay, so again, let's just look at the calculation here. E to the 5.1, because it's the first neuron here, divided by e to the 5.1 plus e to the 2.4 plus e to the 7.8, the sum of this one, and it is 0.063. For the second one is e to the 2.4 divided by the sum of all of that, it's 0.004. Third one is e to the 7.8, which is this one here, divided by the whole value, and 0.933. So if you add up all these values, whatever comes out of the softmax, if you add up all those values, it comes down to 1. So this is kind of interesting, because what it means is that this is a probability distribution of what these values are. So it's basically saying that 93.3%, I believe that, this particular neuron is what is correct for that input, or this particular neuron is what I would classify that input into. With only 0.4%, I would classify it into this second category. And with 6.3%, I would classify it into the top category, or the first category here. So again, it adds up to 100%. So softmax is a very good function because it allows us to take an array and it converts it into another array, which gives you a probability distribution. And from that probability distribution, you pick that particular element within that array, which has the highest probability value, and you say, this is what my predicted category is. Yeah. Okay, now clearly, if you look at this example here, the ground truth value during training says that that input should be classified into the first category, because y true is 1, y true 1 is 1, and the remaining two are 0. But during training, our model predicted that it is going to classify it into the third category. So clearly, there is an error, and we need to fix this error by understanding what is the loss between our training and our ground truth value and the predicted value, which means that you'll need to have a loss function for that. Yes? So what is that loss function? The loss function for multi-class classification is the cross entropy loss function. Remember, in the binary classification, we use the binary cross entropy loss function. In the multi-class classification, we use a superset of that, which is called as the cross entropy loss function. So in the cross entropy loss function, you need to take the ground truth value arrays of y truths. You need to take the softmax outputted array of bipreds. You cannot take the logit values, because what you need to do is you need to convert them into a probability distribution. Remember that this also looks like a probability. The ground truth values also look like a probability distribution. 1, 0, 0. 0, 0 means it is not in that category. The input is not in that category. 1 means that the input is in that category. So you need to take the ground truth value probability distribution, the value emitted by the output function softmax probability distribution, which is your ypred, and then you apply the cross entropy loss, which is what you do here. So when you do that, it's actually quite simple. You take, for example, y true 1, which is the value of 1 here, multiplied with the log of the value for the first element here. So you're doing a 1-to-1 mapping here, right? Y true 1 multiplied by the log of ypred 1 plus y true 2 multiplied by the log of ypred 2, which is this here, y true 3 multiplied by the log of ypred 3, which is here, and then you calculate your loss value, which is minus 2.764. Now we use, just like in every other example, we'll use the gradient descent algorithm and back propagate this loss so that the weights in each of these layers and the neurons in each of these layers gets adjusted, and with sufficient amount of training and enough number of epochs, our loss will converge down into a much smaller value, which is typically 0.001 and so on. But the key takeaways here, the output function for a multi-class classification is softmax, and for the loss function is the cross entropy loss function. Now let's look at a demo of multi-class classification. So here I have created a collab notebook, a Jupyter notebook, which will do multi-class classification. As usual, I start off by importing a few important libraries or modules. Let's do that. So next we will need to generate some data. So here I have created a utility function that will generate some training data for us. Let me go ahead and run this. All right. So, and I'm going to plot our training data. So I have two features, feature one and feature two. And feature one values go from -4 to +4. Similarly, feature two goes from -4 to +4. And remember that in multi-class, you have to have three or more categories. So I have three categories here. First category is I'd like to categorize any value of feature one, feature two, anything that falls, in the, if I were to draw a quadrant, for example, right? The leftmost two quadrants, the left top and the left bottom quadrants, any value that falls within that, I'll classify it as blue. Anything that falls in the top right quadrant, which is this one here, I'll classify it as red. And anything that falls in that bottom right quadrant, I'll classify it as green. Okay, so blue is anything on the left top and bottom blue. Anything on the top right is green, is red, and anything in the bottom right is green. So this is our training data. Okay, now let's go ahead and build our model. So in this model, as you can see, I have two hidden layers and one output layer. The number of neurons in the first hidden layer is 64. I'm using an activation function of ReLU. Input shape is 2 y2 because I have two features that are coming in as input, feature 1 and feature 2. The second hidden layer also I have 64 neurons. I could actually have 32, 64. I'm here to experiment to see which one is the right value. And then I have an activation function of ReLU also for the second hidden layer. And the output layer, I have three neurons. Why do I have three? Because I'm classifying the input features, two input features, feature one and feature two, into three possible categories: the blue category, the red category, or the green category. That's why I have three. So the output function is going to be softmax function, as we had already studied for the multi-class classification use case. Now I'm going to compile the module. I'm going to use the cross entropy loss function. It's also called as a categorical cross entropy loss function because you're classifying it into multiple categories. So categorical cross entropy, another name for cross entropy. Okay, so let me go ahead and compile our model. So we have built our model. Let's go ahead and train. I'm going to pass this training data set that we already generated, and I'm going to run it for 50 bucks. We run it for more. But for the sake of demonstration, I'll keep it at 50. I'm going to use a batch size of 32. Okay. Okay. By the way, when I do a thing here, validation split, what it does is that it takes all these data points that I have, and I have how many data points? Let's go back here. I have 1,000 data points, right? The training data set that I generated. 80% of that it will use for training, and 20% it will use for validation. Okay. That's the reason why I have the split here. Let's go ahead and train our model. So as you can see, it started off with a loss of 0.9252 and it is going down. Right now at the 50th epoch, it has gone to 0.0237. That's pretty good. We have an accuracy of 99.70, which means that, our prediction should be more or less very accurate. Okay, so now what I'll do is that I will generate some data on which we will do the inference. Okay, so I mean, there are some data points, right? So again, remember that just go back here. Any value on feature 1 which is between -4 and 0, and feature 2 -4 and +4 is always going to be blue. And again, right quadrant, right top red, bottom right green, and everything else is blue. Right. Okay, let's go ahead and predict now. So let's make some predictions. Okay, and let's plot our predictions. Let's made some predictions. Let's plot it. So as you can see, anything that is left of this line has to be blue. You can see it's blue. Anything in the top right is going to be red. It is red. Anything in the bottom right is to be green. It is green. And I can add any other feature. Let's say I want to add a feature here, right? Or data point here. Feature 1 is 1 and feature 2 is -3. Okay. So let's add this and see what happens. So I'm going to add to my data point. So feature 1 is 1 and feature 2 is -3. Yeah. 1 and 1 and -3. What do you think it should be colored as this point? It should be colored as green. So let's see if our prediction is correct or not, if our model is able to predict correctly or not. Let's run this again. There you go. It's predicted as green. Let's just take two more examples. Let's say I take -2 and +2 is 1. So it should predict that as blue. And let's say 3 and 3. Okay. -2 and 2 and +3 and 3. Let's add that to our. So I'll say -3 and 3. Sorry, -2 and 2 and +3 and 3. Okay. Let's go ahead and train. Sorry, let's go ahead and make some predictions. Let's plot the predictions. -2 and 2 is blue, and 3 and 3 is red. So as you can see, with just a few lines of code, we are able to create a neural network that can do multi-class classification. It takes inputs and puts it into 3 or more classes. Just as a recap, output function for those kind of neural networks is softmax. The loss function is cross entropy loss function. Okay. Now, let's go ahead and look at another type of classification, multi-label classification. So what is multi-label classification? See, in multi-label classification, as the name suggests, you're trying to assign labels to your input. And you could assign essentially more than one label, zero or more labels, in fact, right, to the incoming input. In multi-class, as contrast, you would essentially be able to slot an input into one of the potential three or more classes. In multi-label, you can have as many classes and you can label each input into zero or more such classes. So what are some good use cases for that? Text categorization. So let's say that's a news article and you'd like to analyze the text and you'd like to classify that as, hey, this news pertains to politics, economy, or international affairs. And it could have multiple. I mean, for example, if there is a UN summit, and you could classify, and there's an article that talks about some economic things that is being studied at at UN at a UN summit, then it would essentially assign a label called economy and international as an example. Image tagging, you would take an image, you essentially have a dog playing, let's say at a beach, and you would like to basically label it as dog, beach, playing, the three labels. Sentiment recognition, you'd like to take a tweet and you would basically like to say it is conservative as well as it is positive. Right. So those are the two labels that you'd like to apply to it. So the key takeaway here is that you have to have a pre-selected list of labels, right? One or more labels. And each input that you're feeding in can simultaneously be assigned zero or more of those labels. Why zero? Because it's quite possible that you might say, hey, it does not fit into any of these labels. And it can assign all the labels too. That's why it's called multi-label classification. So now obvious questions here are, how many neurons do you think would be needed in the output layer? How are these labels represented? Because you have to pass these labels as during your training as ground truth values. How do you represent that? And then what would be the right output function and what would be the loss function? So let's go ahead and study that now. Let's start off with an example. So here I have some news articles, and as ground truth values, I'm basically assigning some labels as well. The first one is I'm assigning a label of politics because it only talks about politics. The second one has if you just look at it, it says innovative robotics technology is transforming industries. Political leaders debate regulations to ensure ethical use in sports and manufacturing. So it could essentially, you're giving it a label of politics as well as technology. You could have also given it a label of sports because it also has this thing called sports, but that's fine. I mean, you're given these two labels. Then you have another article and you're not assigning it any labels and so on and so forth. So potentially there are three labels, right? There is politics, technology, and sports are the three different labels. You build a neural network. So first question, how many neurons do you need in the output layer? You need three. In this particular example, you need three neurons. Why three neurons? Because each neuron corresponds to one of the each neuron corresponds to one of these labels. Yeah. And simultaneously, as we can set, multiple of these labels can get fired up. Okay. And because then you could essentially assign multiple labels to the same input. Similarly, if you look at a picture, or I mean, an example with images, you have one, two, three, four, five particular labels, and you can assign each of these pictures more than one label. For example, if you look at something here, right, this one, this could be having a label of water, it could have a label of people, it could have a label of beach, right? Which means that, by the way, if you look at it, you have one, two, three, four, five labels or five categories. And in this particular example, then the water would lit up. You would have people lighting up, and then beach also lighting up. So that's what you really want to do. So how do you go ahead and build this neural network? Let's look at that. So the first thing here is this is your input, and here are your labels for each of those input. So how do you represent the ground truth values, these labels? Okay. So notice that you can have three possible labels. So I have an array or a vector of three um, elements, and you can essentially assign one or a zero to each of these elements. One means that label exists for that particular input, and zero means it does not. Okay. So if you look at that kind of nomenclature, then for the first input A, your white true vector will look like 1, 0, 0. Why 1, 0, 0? Because it only has this label of politics, right? For the second input B, you have two labels, politics and technology. So you'll essentially have politics lit up to 1, technology light up to 1, and then the last one is lighting up to 0 because it does not have the label of sports. Article 3, none of them are lit up because no label is assigned to it. Article D, you essentially have technology as well as sports light up, and nothing the politics is not lit up. Article E has all three labels. So 111, all of these three labels are lit up. So that's how we essentially pass the ground truth value during training. Now, as we discussed, you need to have as many neurons as there are labels. So you have three labels, you have three neurons, and outcoming from each of these neurons is our standard, uh, logic calculations followed by passing it to an output function. Now let's look at what this output function is. So the output function, I mean, just like the binary classification use case, you would like to light up a neuron to either a 1 or 0, 1 indicating that that label applies, 0 indicating it does not apply, which means that you will need to pass all these inputs or these output neuron values into a sigmoid, because remember that a sigmoid can take any value, negative or positive value, regardless of how small or large it is, and squash it down to a value between 0 and 1. And as long as I can put a threshold and say a value greater than, let's say, 0.75 or whatever is 1, and anything less than that is 0, it actually serves my purpose of lighting up a neuron or not lighting it up. So I take these three output neurons, individually pass each one to its own sigmoid function, and I basically come up with an array or a vector of which will have a 1 or 0. Okay. So let's assume that each of these output neurons logits are, for Z1 is negative 5.2, Z2 is positive 7.4 for this neuron, and Z3 is 4.3. So each of the sigmoid values are, each one, you essentially apply a sigmoid to each of these inputs and you create an array with that. So you apply an sigmoid of negative 5.2, it gives you a value of 0.0055. A sigmoid of 7.4 is 0.994. A sigmoid of 4.3 is 0.986. Yeah, this is how you calculate it. Now, just by looking at this example, you can basically say that this neuron is, I mean, this is a 98.66 percentage is what the sigmoid is saying. This is 99.94, and this is 0.5%, right? So this one you would say is activated, this is activated, this is not activated, correct? Because you're essentially applying a threshold function. And this arbitrary threshold, right? It depends on you. If you think that 0.75 is good, anything greater than 0.75 you would tag it as a 1. Anything less than that you tag it as a 0. So essentially you've taken this array from numeric numbers and you convert it into an array of 0 and 1s. This is great. Now that you have this array 0s and 1s, you can now compare it with this ground truth value array and you can compute the loss. So what is that loss function? Now there are multiple loss functions that you could use here. One is, of course, the binary cross entropy loss function, just like what you had used in the binary classification use case, because you're essentially comparing an output of one, ones and zeros. Yeah. The only difference here is that you're computing it across, multiple arrays, not comparing multiple values, right? The array of 3 here, array of 3 there. There's another thing called weighted cross entropy loss function. There's a third one called focal loss. And I'll explain all these three things right now. And we'll know when to choose which one. Okay, let's start with the binary cross entropy loss function. We had already studied this during binary, classification use case. The formula is pretty simple. You basically take the y truth value, multiply it with the log of the y pred value, add it with 1 minus the y truth value, multiplied with 1 minus the log of the y pred value. That's what it is. And you do that for individual elements in this array. And the reason you need to do that is because unlike in multi-class classification, where you only assign one of the classes to the input, in multi-label you can have 0 or more of these labels being assigned to the input. That's why you need to basically calculate individual losses here. So loss of label 1 is again 1. You see this example here, times the log of y pred 1, which is 0.055 0.0055 plus 1 minus 1 times log of 1 minus this, which is 5.203. Loss of label 2 is 0 times log of this plus 1 minus 0 times log of 1 minus that, which you see here. So loss is 7.4, and label 3 is also computed in the same way. It comes to 0.013. And now you calculate the total loss. You basically add up these three losses and divide it by the number of neurons here, which is 3. So our total loss is 4.212. And now you would use a gradient descent algorithm to go ahead and back propagate this loss so that the weights in each of these neurons gets weights and biases gets updated, and over multiple iterations across multiple epochs, the expectation is that the loss will go down to a very small value, ideally 0.001 and so on. So this is your binary cross entropy loss function, which you already studied during binary classification use case, but it can be used for multi-label classification also. The only change here is that you're doing it for not just one element, one neuron, but multiple neurons, as many neurons as there are labels. Okay, now let's look at what is one challenge with using a plain binary cross entropy loss function. So the first thing is, in real life, data is not uniformly distributed among the labels, and not all labels carry equal importance. What do I mean by that? So let's look at something like this. Okay, so let's say that you're a hospital and you're trying to predict based on different parameters whether a patient has a very rare disease or not. Now, this is your entire population of patient database data that you have in your database, and only 3 of them have this rare disease, right? Let's say 5% of this input patient pool has this disease. Now, all these gray patients who are colored gray, do not have this label assigned, which is 95%. Only the patients who are colored as pink have this disease, which is 5%. Now, as you can see, the disease label, is assigned to a very, very few inputs, whereas the healthy label is assigned to a significantly more inputs. Now, if you use your binary cross entropy, you're not able to focus your attention on what is actually more important here. What is more important here is assigning this label of disease, correct? Even though its occurrence in your entire training data set is less. So you would want to basically figure out a way in which you can give the weightage of a certain label higher, or you give higher weightage to a certain label versus a lower weightage to other labels, even though there are a lot more samples with the other label, right? Just as in this example, healthy, I mean, you have a lot more input with healthy label, 95%, and lot fewer inputs with disease label. That's where your weighted cross entropy loss function comes in. It's basically the same thing as you take your cross entropy loss function and you multiply it with a weight, and you decide what weightage you'd like to assign to each of your incoming labels. Each label will have its own weight. So when you're computing the cross entropy value, you essentially assign, and you remember that you're computing it individually for each labels. You would multiply it with that weight, that label's weight. Okay. Now, how do you assign a weight? There are different strategies. You could use a strategy called inverse frequency, which essentially means that you divide the frequency of occurrence of that label in your training data set. You divide one by that frequency and you assign a label. So if you look at it here, 1 by this particular label will appear 1,000 times in your training. So 1 by 1,000, it is 0.001. Whereas this one here is only there on 10 of the input. So you essentially assign 1 by 10, 0.1. So essentially you're giving, in this particular example, you're giving more weightage to those labels that occur fewer number of times than those labels that occur a lot more times. This is useful in the example that I showed you earlier, where you're trying to assign a label to a patient data, whether they have a rare disease or not. And by the definition of a rare disease, a few people will have it, not a lot. So you would essentially want to weigh that more. That's what this particular strategy does, inverse frequency. Another way of using assigning weights is to use what is called as inverse proportion strategy, where you basically take the max frequency, which is 1,000 in this example here, and divide it with the frequency of its occurrence. I mean, even here, if you notice, the label that has, uh, you know, uh, less occurrence is given more weightage than the label that has a lot more occurrence. There's another one called logarithmic scaling. It basically takes a log of the total number of samples by its frequency. So let's say you have 100,000 samples, you basically divide that 100,000 by the number of samples that have that label and you take its log. You essentially get this same observation here. The label that has a fewer number of such samples, the label that is there to fewer samples is given more weightage than the other ones. But these are different strategies. You can pick whichever strategy you want. But the key takeaway here is that you're assigning a weight so that those labels that do not end up occurring a lot are also treated with importance. And something that occurs a lot more is given less weightage. That's the strategy here. Okay. Now, I mean, this is just a calculation of how this works. I'm not going to walk you through this whole thing, but as you can see, for each label, you multiply the same formula that we used in the past for cross entropy. You multiply it with its weight. And you calculate that. And again, you add up all of the individual losses for each label and you divide it by the total number of labels and you get your total loss. Use the gradient descent to update the weights and biases during back propagation. So this is the focal loss function. And it looks at first glance like the cross entropy loss function with the addition of two new parameters. One is called alpha, the other is called gamma. Both of these are dynamically learned as you're training your neural network. So just like in the weighted cross entropy loss function, where you multiply the cross entropy loss with the weight value, which is essentially fixed, you here in the focal loss function, you multiply it with alpha, which is dynamically calculated as you're training your network, and then you raise the y pred to gamma value. Now, what do these two parameters do? So think about it this way. Let's say you're studying for an exam and there are multiple topics. So ideally, if you know certain topics, you would like to spend less time focusing on those topics and spend more time on topics that that you're not very familiar with. So essentially, you want to balance your attention to those things that are more difficult or for you. And that's what the alpha value does. It's almost like the weight value of the weighted cross entropy loss function. It allows you to pay more attention to the ones that you do not, the topics that you do not know, and less attention to the topics that you know. In our example here, it allows you to focus more attention on, the those samples that have fewer but more important labels, and less importance to, those topics or those labels that are more prevalent in your data set. So in addition to balancing your attention, you also want to figure out how much less attention you want to pay to the topics. If you go back to our, studying example, studying for your test example, you would like to focus, how much less attention do you want to focus on topics that we know very well? And that's what the gamma function allows us to do, so that you don't end up, completely ignoring, the topics that you are already familiar with. If you go back to our studying for an exam use case, or if you go back to the labeling use case for our neural networks, you don't completely ignore those labels that are prevalent in your data set. You do pay attention to that, but you reduce the influence of those examples or those labels. So that's what your focal loss function does. And as you can see, right, as you're getting trained, because these are, as you're training a neural network, because these are trainable parameters, both alpha and gamma are continuously learned. Because in addition to adjusting your weight and bias values during the propagation, you also adjust the alpha and gamma values. That's how they essentially are, they are learned as part of the training. So again, in a nutshell, if you look at the multi-label classification use case, you would use softmax as your output function, and you would use multiple types of cross entropy loss functions, whether it is straight direct cross entropy loss function, or you would use the weighted cross entropy loss function or the focal loss function. Now let's look at an example. So what we will do here is we are going to use some text strings and corresponding labels that you would assign to each of these text strings. So this is going to be our input. For example, let's look at this. It says the gallery hosted an exhibition featuring paintings of basketball players. Given that it has gallery and paintings, you would like to assign it a label called art. And because it also has basketball players, we would like to assign it a label called sports. Similarly, let's take another sentence. The government new policy aims to reduce unemployment. This looks like an article or a topic related to politics. I'm going to assign it a label politics. So what I've done here is I have a few, you know, uh, training samples, some text and corresponding labels associated with each of those texts. So let's run that. Now, let me also have some utility functions that is going to pre-process this data before we can use it to train our neural network. Why do we have to pre-process? Because neural networks only understand numbers, and here we have textual information. So first thing that we need to do is we have to take this text and convert it into numbers, an array of numbers to be more specific. So let's not go into the specifics of these utility functions. You can look at them offline when I share the GitHub link for the code. But let me run this first. Okay, so I run that. And what I've done here, let's actually start with inspecting what we have done here. So the first thing is the labels. I looked at all the training samples and I identified what are the unique labels that are there in this training set. And there are 4 unique labels: art, sports, politics, and technology. The fact that there are 4 labels, we already know that we need to have 4 neurons in our output layer. That part is very clear. But because neural networks only understand numbers, I need to convert these into numbers. So one way to do that is to use essentially one hot encoding of strings. What I mean by that is, because there are 4 labels, let's say that I want to represent each of these labels as an array or a vector of 4 integers. And so for example, art, I can express it as an array of 1, 0, 0, 0. Why 4? Because there are 4 labels. Sports, I'll encode as 0, 1, 0, 0. Politics as 0, 0, 1, 0. Technology as 0, 0, 0, 1. So what it essentially means is that if a label is there, I turn it to 1. If it is not there, I turn it to 0. So if you have 2 labels, for example, arts and sports, I will turn on their specific bits to 1. So art is 1 here, the first element in the array. So I turn that to 1. Sports is the second element. I turn that to 1. And because politics and technology are not there, essentially in our example here, so I put them as zeros here. If I had 3 labels, I would do that. So art, politics, and technology. Art is 1, politics is 0, art is 1, sports is 0, politics is 1, and technology is 1. So this is how I can encode textual information. We'll learn more about one-hot encoding later on, but for now, just go with this flow. Now, each sentence also I pre-processed. I need to convert them into textual information. So what I do here is, again, I use one-hot encoding. So what I do here is I gather all the sentences in my training data set, and I create a unique list of all the words. And for each word, I'll assign it a number. So think about it like I have an array into which I put each of these unique words, and the position of a word in that array, its index becomes its number. Okay. So I take this. In the first sentence, the gallery hosted an exhibition featuring paintings of basketball players. And we know the word the occupies the first slot in our array of unique words. The word gallery occupies the 22nd in index in our array, and hosted 54th, and so on. Now, once you have this, I can essentially do a one hot encoding. And the way I do that is I'll figure out how many unique words I have, and I will create those many number of uh, elements in my array. And for each word, I'll just turn on the bit that basically has that word. So as we said, the occupies the index 1 in my array. So I essentially turn that on here to 1. The word gallery occupies the 22nd index in my array. So for the second token, somewhere here is the 22nd index. I turn that as 1. Everything else remains 0. So this is one hot encoding. We don't have to go into the specifics to understand multi-label classification. So just go with the flow that there is a technique in which you can take input strings and convert them into numbers and use that to train our neural networks. So I do that for all the sentences, and let me okay, now let's go and build our neural network. Okay. By the way, if we just look at a summary of what we have processed so far, the number of samples we have in our training data set is 35. The number of unique words is 171. The number of labels is 4. Okay. So now what we do is we build our neural network. So the way we build our neural network is we basically pass the input. We flatten the input. The reason we flatten it, again, without going into the specifics of text processing, remember that this is not just one input. It's a series of words. And each word is represented as a vector, one hot encoded vector with a bit turned on for the word for that word, and everything else remains 0. Go to the next word. If you turn on a bit based on the index for that word in our unique vocabulary list, turn that on, everything else becomes 0. Go to the next one, and so on. So essentially, you have this big set of array of vectors, if you will. Now you want to flatten that so that you can essentially pass it as one big array. Yeah, the two-dimensional array can be flattened by folding all the columns to the rows, and then you create a very massive sized flattened array. That's all I'm doing with by calling flatten here. So I pass that in as my input. I create one dense layer, one hidden layer with 64 neurons in it, and I use ReLU activation function. Now, how many neurons should be there in the output layer? As many as unique labels, because that is what we'd like to assign to each of these inputs. So because there are 4 unique labels, I essentially have 4 as my number of neurons in my output layer. Now we are using, as we studied earlier, the sigmoid activation function. What we want to do is that for any given text, we'd like to use sigmoid, which allows us to squish any number between 0 and 1, which can be used as a way to look at it as a probability that that label can be applied. So you can turn that into a value, either a 0 value or a 1 value based on the threshold. We discussed this earlier. So we use the activation function or the output function as sigmoid here. Now we compile our neural network. I'm going to use binary cross entropy as our loss function. Let's go ahead and run that. Now that our model is built, let's train it. We're going to pass the input that we gathered up there, and then we train it for 1,000 epochs with the batch size of 32. Let's go ahead and train it. So we start with the loss value of 0.6938. As we are going ahead with training, the loss, as you can see, is continuously decreasing, which is good, which means that our neural network is actually learning. Let's keep going. Let's wait for it to hit our 1,000th epoch. Um, it's going to take some time because we're doing 1,000 epochs. And again, one of the reasons why we're doing 1,000 epochs is because we want to really, this text information. There's a lot of, I mean, the input size is pretty big, so it's good to train for a much larger number of iterations. So we'll wait for it to completely train. All right. So we have run this through 1,000 epochs. We see that the loss value is actually very, very small, which is great. Now let's go ahead and start doing some predictions. And the way I'd like to do this predictions is, again, essentially called model.predict, but I'll give it some sample input strings, and we will have our neural network predict the labels. And obviously, the way it'll predict the labels is it's going to, again, we'll use the same thing. We'll tokenize this input string as one hot encoded vector when you pass that as the input to a prediction, and it will emit a matrix for the label. And what we'll say is that if the value is greater than, after sigmoid function is applied, is greater than zero point 0.5, we'll say, yeah, that label exists, and we will essentially convert that one hot encoded label matrix into string. Okay, so let's run this. Let's do some predictions. And as you can see, it said the gallery hosted an exhibition featuring paintings of basketball players, arts and sports, which is correct. The government is investing heavily in AI and blockchain technology. Obviously, because there's a word government, it did assign it a label politics. Because it had AI and blockchain, it applied the word technology. Never did you actually go and train your neural network to say, if you find this word called AI and blockchain, put it as technology. What you did instead is that you essentially gave it a bunch of strings that presumably had these words to which those labels were applied. And when you give it a completely new sentence, it basically applies, those labels back. So here I have third example as Michael plays basketball while Bill builds AI robots that would be used by the government. Now here it has labeled it as sports and technology. Clearly because basketball is there, I think it identified that sports makes a good label for that. AI is there, so technology. The word government is there. Maybe it should have also applied the label politics, but again, we use only 35 samples in our training data set. If you have used thousands and sometimes tens and thousands, the predictions will start to get better. That's why I think the size of your data set is quite critical in getting very good predictions. But even with a very small data set, we actually saw that our neural network is able to apply the right labels. And as you can see, it can apply multiple labels to the same input. That's the reason why it's called multi-class classification. To summarize, for multi-label classification, we use the sigmoid as our output layer's output function. And we can use one of these different loss function, binary cross entropy, weighted cross entropy, or focal loss. And our model is defined as something like this: as many neurons in the output layer as there are unique labels, and we use the loss function as specified here. Now let's look at another use case that can be solved through neural networks: ranking. So in ranking, what we do is that we take as input an array, and we want the neural network to learn how to rank the elements of the array in order of preference between a value of 1 and n. If there are n elements in your array, between a value of 1 and n. So what are some typical use cases? For example, in a search engine, let's say the search engine produces 4 answers, and you would like to build a neural network that can learn how to rank these 4 answers so that the best answer is essentially presented to the end user. So you could essentially train it by first, a human ranking those answers and giving the answers as well as the ranking to the neural network so the neural network learns. So in production, you can essentially use the trained neural network to rank your answers. So, I mean, LLMs or large language models use this quite frequently. Now, the key point here to remember is that each element in our array is given a rank between 1 and n. Okay. Now, obvious questions. How many neurons do you think are there in the output layer? First of all, because you're doing ranking, you also need to know how ranks are represented and what would be the right output function and what would be a good loss function. Now, let's look at that. Now, let's look at the ranking use case in more detail. So, here I have a neural network, and what I'm passing in as input is a query. The query, as an example, is what is the best programming language? And as again, the assumption here is that you're trying to rank answers from a search engine. And the response, basically, the result for that query is JavaScript, C, Rust, and Python, just as an example. Now, the combination of your query and results is your input, right? The query that the search engine takes and the answers that it produces. Now, what you'd like to also pass as a ground truth value of the ranking. And here I have C, Rust, Python, and JavaScript. So essentially, these four I rank as C is 4, highest ranked, Rust is the next one at 3, Python is at 2, and JavaScript is at 1. So this is my ranking. Now, clearly, because I'd like to rank elements of 4, I want to have as many neurons here in the output layer. So there are 4 neurons here in the output layer. Each one is basically emitting a value ypred 1, ypred 2, ypred 3, and ypred 4. Okay. Now, if you're building a system that can that has more things that you would like to rank, then you would have as many such neurons here. Okay. Before we get into understanding the output function and loss function for ranking use case, let's try to understand a little bit more about ranking because it is somewhat different than classification and prediction use cases. So let's say that this is our ground truth value, right? The results are C, Rust, Python, and JavaScript. C is ranked the highest at 4, followed by Rust at 3, Python following that at 2, and JavaScript at 1. Now let's assume that we have these 5 different other ranks that are predicted. Okay. Now, which of these 5 do you think is the closest to this ground truth value? Maybe you can start with the top highest ranked one. So you can see C and E have 4 at the first for the first item, which is the same as the one for the ground truth value. Now, so you can say, okay, I have already subsetted my results into, you know, C and E. Now you go to the next one, you say, okay, C has 3 for the second item, which is the same as the ground truth value. However, E has 2. So maybe my preference is towards C. But then when you go to the next item, C has 1, whereas the ground truth is supposed to have 2. And you can see that E has 3, whereas the ground truth is supposed to have 2. And then when you go to the next one, C has 2, ground truth is 1, and E is 1. So which of these things do you think is better or more closely related to the ground truth value? Just taking relative differences between individual ranks do not work because if you say I'll look at the ground truth value and subtract from it the value that is there in the predicted value. So let's use an example to see this. Let's say my prediction here is 3, ground truth value is 4. So I do 4 minus 3 is 1. Prediction is 2, prediction is 2, ground truth is 3. 3 minus 2 is 1. Prediction is 1, ground truth is 2. 2 minus 1 is 1. Prediction is 4, ground truth is 1. 1 minus 4 is minus 3. If you add all of them up, it sums up to 0. But it sums up to 0 for any of my predictions. So I cannot definitely I cannot use the differences between individual ranks. So how do I solve for this? So one way to solve for this is to basically use a technique called as normalized discounted cumulative gain. So this will allow us to figure out, how to qualify whether our ranking from our neural network is good or not, or how close is it to our ground truth value. Okay. So the key idea behind normalized discounted cumulative gain, we'll also call it NDCG, is that highly relevant items should appear at the top of the rank list. So essentially, you're ordering your items in your list in order of top being the highest and bottom being the lowest in terms of its ranking. Okay. Um, and obviously, the relevance goes down as you're going down the list. Now, normalized discounted cumulative gain is made up of three components. The first is called DCG, which is discounted cumulative gain. We'll look at what that is in a minute. The second one is called as ideal DCG. And then finally, it's called normalized DCG. Okay, so let's look at that. Now, we'll use our same example here. This is our ground truth value. And let's assume that these are the different predicted ranking values. Okay, and we'd like to find out which of these is as closely related to the ground truth value. So first thing is we produce what is called as a discounted cumulative gain for each of these predicted values. Okay, so the way we do that is using the formula that is shown here. So let's take an example. So for the ranking prediction A, the DCG is calculated as 2 raised to the rank is what? In this case is 3 here. Subtract 1 from that, and then divided by the log of the position of the item and add 1 to it. And do that for each and every item in your list. So let's look at this as an example. So you take 2, the first item in our list is 3, so you raise 2 to the 3 minus 1 divided by log of 1. This position is 1, this position is 2, this position is 3, and this position is 4. So you do log of 1 plus 1. Then you add that to the second item. Its rank is 2, so you say 2 raised to 2 minus 1 divided by its position is 2, log of 2 plus 1. Add that with the next item. Its rank is 1, so you do 2 raised to 1 minus 1 divided by its position is 3, log of 3 plus 1. And the final item, its position is 4, its rank is also 4, so you say 2 raised to the rank, which is 4, minus 1 divided by log of its position, which is 4 plus 1. So when you add all of this, you get 22.871. Okay, so now you've taken an array and you have squashed it into one numeric scalar value. But one way of looking at it is the following. If you look at what's happening here, as we said, the ranking here is in order of preference, right? So what your DCG algorithm does is that as the position increases, it discounts the value of its score or rank by that much. That's the reason why you divide it by the position, log of the position. Okay. And that's what the DCG algorithm does. Now let's calculate the DCG for the other four rankings. So for B, we do the same thing, 2 raised to 1 minus 1 divided by the log of 1, which is the position 1 plus 1, 2 raised 2 minus 1, log of 2 plus 1, and so on. And each one produces a different scalar value. Now what we do next is we calculate what is called as an ideal discounted cumulative gain. And that is for the ideal is what the ground truth value says. The same formula, exact same formula. 2 raised to 4 divided by 2 raised to 4 minus 1 divided by the log of its position 1 plus 1. 2 raised to 3 minus 1 divided by log its position is 2 plus 1 and so on. Now it produces a value 30.797. Okay. Now you have it for the ideal DCG, which is for the ground truth value, and you have the DCG for the individual predictions. Now you take the normalized value of that. That's where it comes, normalized discounted cumulative gain. The way you normalize is that you take your predicted DCGs and your ideal DCG. You divide your predicted DCG with your ideal DCG for each one, and then you get again individual values, numeric values, and you pick the one that has the highest of this, 0.994, which is for rank C. Now you know that this array is more close to this ground truth value array than all the other predictions. So this is the general concept of normalized discounted cumulative gain, NDCG. Okay. Now let's go back to our neural network. So in our neural network, again we have our ground truth value that is basically an array of different items with their ranking. So you have to have as many neurons as we discussed earlier, right? As many neurons as there are ranks. So there are 4 ranks, we have 4 neurons. And we would apply the linear output function. So we'll take the values from Z1, Z2, Z3, and Z4, which are of course calculated like this. And we'll apply the linear function and get the individual values for ypred1, ypred2, ypred3, ypred4. So here ypred1 is 0.4, 0.8 is ypred2, 0.2 is ypred3, and 0.6 is ypred4. What should it have been? It should have been 4, 3, 2, 1, whereas our neural network, while in its training phase, is predicting as 0.4, 0.8, 0.2, and 0.6, which is fine. But we now need to take these two, the ground truth value y truth and predicted value y pred, pass it through a loss function, and then compute the loss. So there are multiple types of loss functions that you could use for ranking. There is a thing called list net loss. There is a thing called approximate normalized discounted cumulative gain loss. There's a thing called list-wise hinge loss, and so on. We will look at list net loss here. Okay. So how does list net loss function work? So you have your ground truth value in green, which is your y true. You have your predicted value in blue. Okay. The first step is to create a softmax. Remember what a softmax does? It takes this array and it converts each of these individual numbers uh, based on a probability distribution across this array. Okay? So the formula is very straightforward. You do e raised to the power 4. You do that for the ground truth value first because you want to compare two lists. So you have to convert both those lists into the similar form. So you're converting both of this input ground truth value array into softmax and as well as the predicted ground truth value also into its own individual softmax. That will allow us to compare. So you compare. So you essentially do e raised to the power 4, y4, because the rank is 4, divided by the sum of e raised to the 4, e raised to the 2, e raised to the 2, 3, 2, and 1. We do that for the next one and so on. So essentially, this is what we get. We repeat the same thing for the predicted values. E raised to the 0.4 divided by e raised to the 0.4 plus e raised to the 0.8 plus e raised to the 0.2 plus e raised to the 0.6. You get 0.220 and so on. Notice that what the softmax function does is that it converts it into these numbers, but when you add up all these numbers, it adds up to 1. So think about this as a probability distribution. And this also same thing, it adds up to 1. So step 2 of your list net loss function is now to use the list net loss function, which basically allows you to compare the probability distributions of two different lists. Okay. The formula is very straightforward. You take the first probability from a ground truth, multiply it with the log of the probability from your prediction. And then you do that for each and every item in your list and add them up. That's all you do. So now you have a loss of 1.427. Now we take our loss value and we back propagate this through our neural network using the gradient descent algorithm so that the weights and biases of the individual neurons in each of these layers gets adjusted so that subsequent prediction starts to get better. And over time, with sufficient amount of training, we'll start to predict, the ranking accurately. Now let's look at another loss function. This is called the adjusted normalized discounted cumulative gain loss function. I already showed you how normalized discounted cumulative gain works, but now let's see what would be a loss function that is modeled after that particular technique. So let's say that we have again the ground truth value ranking is this and the predicted ranking is this. But notice that in this example, what I have is the ground truth value numbers are also not sorted. So Python is ranked at 3, Rust is ranked at 4, and C is ranked at 2, and JavaScript is at 1. See, this is not in a sorted order. And if you remember, the NDCG algorithm actually requires that the list be first sorted in order of relevance. Highest relevant item at the top and the lowest one at the bottom. But let's say we have an array like this in the ground truth value, and the prediction is this. The first step when doing adjusted NDCG is to first sort the ground truth value results. So we sort it this way. So you basically say the highest ranked item goes to the top, Rust is 4, Python goes next, which is 3, C goes next, which is 2, and JavaScript is at 1. Now we do a similar sorting of the predicted values as well. So here the highest ranked value is 0.4, so we keep Python at 0.4, that is what it was predicted. Our C comes in next at 0.3, Rust following it at 0.2, and JavaScript at 0.1. As a quick reminder, the the discounted cumulative score is calculated by adding up basically this thing, which is 2 raised to the rank, right? Or this minus 1 divided by the position of that particular element in the array. This is one first position, second position, third position, fourth position. Similarly, here, first position, second position, third position, fourth position. And you add up everything. And the adjusted NDCG loss is calculated by calculating the DCG of ypred. Essentially, feed all this into that, all the predictions into this formula, divided by the DCG of ytrue. Same thing, feed all this data into this formula, and then you get the adjusted NDCG loss. So I implemented this in using NumPy so that you can just quickly see what the value would be. So it's a pretty straightforward implementation. You essentially sort the list first. I'm passing, by the way, these are my two arrays. So the first one is ytrue, where I have 3, 4, 2, 1, 3, 4, 2, 1. And then I have the prediction 0.4, 0.2, 0.3, 0.1, 4, 0.4, 0.2, 0.3, and 0.1. Now pass it to my function. The first thing, as we discussed earlier, is to sort. I've sorted this list. Then I calculate the DCG of my ytrue using this formula. Then again, I sort the uh, ypreds, and I calculate the DCG of that. I divide the DCG of pred and divide it by the DCG of ytrue, and then we essentially return the loss function. Now let's look at a demo of how to build a neural network that can be trained to do ranking. Let's build a neural network that will figure out how to rank movies. So what I will do here is, just like in our prior examples, I'm going to import some of the important required Python modules. I've done that. So one thing that you notice here is that I'm also installing this particular module called TensorFlow Ranking, because this will allow us to import the what is called as an adjusted normalized discounted cumulative gain loss function, and use that as a loss function in our model. So let's start with data generation first. So I'm creating some synthetic data. So this is a list of movie names: Shawshank Redemption, Godfather, Dark Knight, Pulp Fiction, RRR, Bahubali, Iga, KGF, Lord of the Rings, and so on. And what I will do here is that I will randomly assign some rankings to each of these movies, and I will take this data in sets of four. So four movie names randomly, and as you can see here, and then I'm going to assign random ranks to each of these four movies. In an ideal scenario, you should essentially get real rankings, maybe from a website like IMDb. Anyway, so what I'm doing here is generating some synthetic data. Let's go ahead and run that. And as you can see here, it basically, let's go back here. For the four randomly selected movie, Jurassic Park, it gives it a rank of 3, Whiplash a rank of 4, which is the highest, and Departed a rank of 1, and KGF a rank of 2. The second sample for our training sample would be Inception ranked at 4, Parasite at 1, RRR at 2, and Bahubali at 3. So that's our synthetic data that we'll feed to our neural network. Okay, now again, like we studied earlier, you cannot pass textual information to a neural network. A neural network only understands numeric data. So one way to convert text to numbers is using one hot encoding. We will not go into the specifics of how that is done in this episode. That is covered in subsequent seasons. So we'll cover it there. But for now, just think about it this way. There is a method through which you can convert text to numbers. And in this specific case, it's going to be an array of numbers. So let's run that, and we are going to convert our input into numbers. And what we have done here is that we have also split our entire sample set into training sample set as well as test sample set. And we'll pass the training sample set to our neural network. Let's go ahead and build the neural network now. So let's go and build that. Okay. So let's go ahead and build the neural network. So in the neural network, I'm creating a sequential neural network using the Keras library. And I have three hidden layers. In the first hidden layer, I have 64 neurons. Activation function is ReLU. Second hidden layer also has 32 neurons, and activation function is also ReLU. The third one is 16 neurons, and again, activation function is ReLU. ReLU happens to be a very popular activation function these days. So I think it's good to start off with ReLU as your default activation function for many use cases. That's why I use ReLU here. Now on the final output layer, because we are ranking four movies at a time, we need to have four values that are emitted. So I'm using four neurons in my output layer, and the activation function I'm using is softmax. Now what I do here is I compile my model. I'm using the optimizer. Now for the loss function, I'm using the approximate NDCG loss function. Yeah. And let's go ahead and build our model as well as feed the training data to our model. And let's start our training. So our training is going through multiple epochs. We are training it for 100 epochs with a batch size of 4. Let's go ahead. Okay, it's done with the training. I mean, our loss has not really converged down to a very small number. It should ideally be 0.001. It has not. I think one of the primary reasons for that is, first of all, our training data set is very small. And more importantly, we are using some random functions to assign ranks. So, I mean, I mean, learning a real pattern from random data is essentially not that easy, sometimes impossible. So again, and what we are trying to accomplish here is to demonstrate how to use Keras libraries to build a model to rank. So let's not focus on converging the loss down to zero because we really don't have realistic data set. But for now, let's go with this. Now what I'll do is I'm going to give it a bunch of other movie names, and let's see how it ranks. So let's go ahead and run this. Okay, so I've given it four movie names: Interstellar, Parasite, RRR, and KGF. When we generated our synthetic data, the rankings that we had assigned is for Interstellar, we had assigned a rank of 4, Parasite as 3, RRR as 1, and KGF as 2. Our model has predicted Interstellar at 4. Parasite, it did not predict it correctly. It should have been 3. It's predicted as 1. Again, because our loss is not really converged to a very small number. And so on, right? And again, the next set of movies: Pulp Fiction, Lion King, Fight Club, and Jurassic Park. These are the actual ranks, and this is what the model predicted. So going back to looking at our model architecture again, as you can see, it's a very simple model architecture. You have a bunch of hidden layers, and then you have an output layer with as many neurons as the ranks that you would like to derive or predict. The output function is softmax, and the loss function you're using is approx NDCG loss function. So to conclude, these are the different use cases that we have studied today. Regression use case, where you're predicting a number, and what we studied is that the output function we'll use in the output layer is a linear function, and the loss function is something like a mean squared error loss function. For classification, depending on the type of classification, for binary classification, we'd use sigmoid as our output layer function, and we'll use binary cross entropy as our loss function. For multi-class, we use softmax as our output function and cross entropy or categorical cross entropy as our loss function. For multi-label classification, for as many labels there are in our output layer, we'll use sigmoid for each one of those. And we could use again a variety of different loss functions like binary weighted cross entropy loss function, focal loss function, and so on. For ranking, we saw that we could either use softmax or a linear output function with listnet or adjusted normalized discounted cumulative gain as our loss function. And then generation. So I'm skipping generation in this episode because generation requires us to understand the transformer architecture, which is an advanced topic, as well as large language models. So I will be covering that in our season 4 of our web series, and we'll see how we can essentially generate text given an input string, and how do you train a neural network to do that. So this concludes our episode. And what we will study in our next episode, which is season 1, episode 3, is the other part of our neural network, which is how do you tune the hidden layers? How do you initialize weights? What would be the different activation functions that you could use in the hidden layers? We'll also learn some techniques on speeding up gradient descent because, as you remember, gradient descent is the cornerstone of how neural networks can learn by adjusting their weights. We'll talk about different techniques in which you can optimize that. We already seen the use of things like Adam in some of the demos that I showed you in episode 2, this episode, but we'll actually understand this a little bit more in episode 3. And we'll also finally study in episode 3 how do you avoid over and underfitting so that you can do better predictions. So thank you for listening to episode 2 of season 1. Until next time, happy learning.